So same as before, we'll look at this as an example of integration using integration by parts. And I'll talk about why we use integration by parts. And then at the end, again, we'll go through and then just jot down the steps involved with this so that might be something to review, as part of your revision process. First thing I would do with this was think of it as not written like that, but written as the integral of 4x times e to the minus 3x, because again, if I've got a division divided by e to the 3x, that could just as easily be written as times e to the minus 3x, because the inverse is the negative power. Algebraic substitution won't work in this case. There's nothing I can really call u. If I decided to let u equal e to the minus 3x, for example, and differentiated that, I'd still have the e to the minus 3x terms there. And so there's no e to the minus 3x outside that before allowed us to cancel it out. So what I have is a situation where I've got my variable that I want to get rid of, or integrate rather, appearing twice. So in differentiation, if I had a function to differentiate where x appeared twice, I'd have to use the product rule. The integration by parts rule that you've got on your data sheet looks like this. Integral u dv equals uv minus integral v du in shorthand terms. That's the integration by parts rule. Tells us that I divide my original integral into two parts. I'm going to call one part u and one part dv. I've got two parts here, the 4x and the e to the minus 3x. And then whatever I call u, I'm going to differentiate because I need du here. Whatever I call dv, I need to integrate because I need v there. So it's a case of deciding which bit to call u and which bit to call dv. The whole point of this method is that I've turned this integral of u dv into an integral of v du. In other words, it's the integral of whatever I've called dv, it's the integral of that, and whatever I've called u, it's the differential of that. So what you do is you look at your original function and think, if I call that u, the 4x, I've got to differentiate it to get to u. And when I differentiate 4x, the x disappears. So that means I'm then left with an integral where x is gone. So it's going to work. And if we look at the textbook, at the questions, just find them. If we look at the textbook on page 488 and look at some of these, we'll see in number 1. Actually, let me just put this in the notes so I can play with it. So if we look at number 1, for example, here, I'm going to call one bit of this u, one bit dv, as we've just been talking about. If I let u equal x, then I differentiate that, the x will disappear, so it's going to work. That's the one we're just going to look at now. This one, I'm going to let one bit equal u and one bit equal dv. It's no good letting the sine x equal u, because if I differentiate sine x, it just becomes cos x, it doesn't disappear, and vice versa. If I've got a cos x, or cos 2 theta, it's no good letting that equal u, because it doesn't disappear when I differentiate it. So I let the x equal u, because when I differentiate it, it disappears. I let u equal 5 theta, because when I differentiate it, the theta disappears. And if you look at some of the others, this one, bit of a problem, because if I let 3t squared equal u and differentiate it, doesn't disappear. So in that case, I have to actually apply the method twice. I apply it once, and then when I differentiate it, I get 6t, and I apply it again, and then the 2 disappears. So that's quite a long-winded process. So you're not going to get one like that in the exam, because it's just a case of doing the same thing more than once, so it will take you a while. Look down at these other ones, I think you could see that would let u equal 2x there, I'd let u equal x there, I'd let u equal t squared there, but then no, I've got to go through it twice. So that's the idea. So let's look through at one particular question, this question here, the one we've just been looking at. And again, we'll go through the method and then we'll come back at the end and look right down the steps. So, I'm going to let u equal in this case 4x. And you don't have to set it out this way, but then that means dv has got to equal the other bit, which is e to the minus 3x. So now the bit that I call u, I'm going to have to differentiate to get du by dx. The bit I call dv, I'm going to have to integrate to get v. And hopefully that's going to be a standard integral, so all you've got to do is look at the table of standard integrals, and this will be a standard differential. So u by dx, we can just write down the answer. It's 4. And dv, if I integrate that, it stays as e to the minus 3x, but the number comes out and goes underneath. So this v will equal minus a third, effectively, e to the minus 3x. So the minus 3 comes out and goes underneath. So now I just put them into this. I'll replace my original integral, so that's my original integral, effectively, the left-hand side. So what I'm interested in is putting these values here into that little recipe. So u will be this, v will be this, and so on. So see if you can carry on and finish it, but I'll carry on here. So we're left with the integral over u dv, our original integral in other words, 4x e to the minus 3x, becomes u, which is 4x, times the integral of dv, or v, which is minus a third of e to the minus 3x, minus the integral v, which is minus a third of e to the minus 3x times du, which is 4. Nearly ran out of room. I should have left myself a bit more room there. Just have a look at it, check you see what's going on there. It's well worth using brackets, certainly initially, because then you can see that's the u bit, that's the v bit, and that's the v, and that's the du bit.
Tidy that up now.
Yeah, you can, definitely. And it's certainly worth doing that because we've got negatives in here, and so we can tidy up. So what does that finally equal? Minus 4 over 3 x e to the minus 3x minus this integral, a third, well, times 4, so that's 4/3 e to the minus 3x dx. And we're left with this, what we can do. The original, this x in the original integral here has disappeared now, so it's basically just got a standard integral to do. The 4/3 could come outside the integral and it's just integral e to the minus 3x, which is minus 4. Minus 4/3 integral e to the minus 3x dx. Leave yourself with your standard integral, so you can now look at your table. Oops.
Is that not plus 4/3?
No.
No.
What was it? Have I made a mistake? V was minus a third, so you're right, James. There should be a minus a third inside there. Well done. which means that should be minus, so that makes it out plus, yes, you're right. Plus 4/3. Minus 4/3 x e to the minus 3x plus 4/3, and this is again minus 1/3 e to the minus 3x, and then at the end plus c. You could tidy up algebraically here, and there's no harm in doing that, and as far as the exam is concerned. I could combine these two fractions here to get minus 4/3 and 9, but if you leave it like this, you can see that the 4/3 is common to both, as is e to the minus 3x. So I could take those outside the bracket and tidy right up. If I took minus 4/3 e to the minus 3x outside the bracket, I ask myself, what have I got to times this by now to get back to this? Well, the only thing that's missing is the x, so it's just x here. What have I got to times minus 4/3 e to the minus 3x to get back to this again? Just the 1/3, isn't it? Plus 1/3. So it'll be plus 1/3 plus c. If you've not tidied it up perfectly, or you've made a small mistake when you tidy up, well, then you won't lose marks really, because you've done the integral correctly. You can only gain marks by correctly tidying up. So what are the steps involved with this integration by parts? And so if you look back at the beginning, get the first step, recognising that we need to use integration by parts. So we've got two functions multiplied together. In other words, x appears twice, and we can't combine the two functions together. Let's look at the original problem. We can't combine these two, consolidate it, in other words, and we can't use algebraic substitution and make x disappear. So we've got two separate functions, the 4x and the e to the minus 3x, very like when we differentiate the product rule. In fact, this partial fractions, this by parts rule comes from the product rule. So we recognise, first of all, that we need to use this method. We've got two functions multiplied together. So that's step one. What's the next step? So step two, decide what you're going to call u and what you're going to call dv. Remembering that whatever you call u, you're going to differentiate, and hopefully, as we've discussed at that point, the reason x disappears. If not, if I apply it twice, will it disappear? 3 times, will it disappear? So it can get long-winded, but it will work. In the exam, it will disappear first time through. Okay, so that's step two. What's next? So step three, whatever we call u, we differentiate to get du, and whatever we call dv, we integrate to get v. Then step four, plug them into the formula. So plug them into the formula, and hopefully that leaves you with a standard integral to do at the end. X is disappearing, and you can see the final answer. And then tidy up if you can.